Ladies and gentlemen, it's with great honor that we welcome you to the 38th installment of the proudly presented inaugural lecture series organized by the Faculty of Graduate Studies of the University of Moratuwa. To formally commence today's proceedings, let me invite Dr. Ranga Rodrigo from the University of Moratuwa to introduce our professor for the day. Samarasinghe from the Department of Electronics and Telecommunication Engineering of the Faculty of Engineering at the University of Moratuwa.
Tharaka Samarasinghe, an illustrious alumnus of Ananda College, obtained his BSc Engineering Honours degree in Electronic and Telecommunication Engineering from the University of Moratuwa, Sri Lanka, graduating with first class honours in 2008. He was awarded the prestigious gold medal for the most outstanding undergraduate of the university. He began his career as a radio network design, planning and optimization engineer at Mobitel Private Limited in 2009. He joined the University of Melbourne to pursue postgraduate studies and obtained his PhD degree in 2012. His research interests span wireless communication, information theory, and intelligent networking and transport systems. His contributions include advances in opportunistic beamforming and cellular network optimization, wireless energy transfer and beamforming techniques, and physical layer security. More recently, he has explored UAV-assisted communications for disaster resilience and vehicular networks. With over 740 citations and 50 publications, his research has significantly advanced the academic and practical impact, bridging theoretical insights in the real-world challenging modern communication systems. Since January 2015, he has been with the Department of Electronic and Telecommunication Engineering, University of Moratuwa, as a senior lecturer, and in 2024, he was appointed professor in the same department. He also serves as the head of the Department of Medical Technology at the Faculty of Medicine, University of Moratuwa. Professor Samarasinghe is a corporate member of the Institution of Engineers Sri Lanka, a senior member and the Sri Lanka section's chairman-elect of the Institute of Electrical and Electronics Engineers, USA, an honorary fellow in the Department of Electrical and Electronic Engineering at the University of Melbourne. Professor.
Thank you, Dr. Rodrigo. Good afternoon, everyone. Welcome to the 38th lecture of the inaugural lecture series. I'm Tharaka Samarasinghe, and my lecture is on how cars talk to each other, which leads to the future of safer roads. Starting with an outline of my lecture, I will first introduce what vehicle-to-vehicle communication is, advantages of vehicle-to-vehicle communications, the well-known technologies that we use for vehicle-to-vehicle communications, and then I wind up with some of the interesting work that we have done at the university on vehicle-to-vehicle communications. All of us understand that road safety is crucial, and 94%, it's known that 94% of the accidents involve human error. Now, road network is a resource where multiple people share the resource, and when multiple people share a resource, conflict in a vehicular network, what eventually happens is accidents, which affects the road safety. Now, to eliminate conflict in social levels, the main thing that we usually do is to improve communication among the stakeholders. Now, what vehicle-to-vehicle communication does is to do this at the vehicle level so that transparent to the drivers, the vehicles talk to each other, so that the information flow between the vehicles can be utilized to improve safety in the road network. Actually, there are many other benefits, but the main goal being, can we use the information transfer among the vehicles in an autonomous manner to improve the road safety or overall improve our transportation experience. Now, vehicular communication introduced this concept of what you call a VAN, a vehicular ad hoc network. So when you look at a VANET, which you can see in a picture here, there's different information flows. Now here you can see communication among two vehicles, communication among a vehicle and a roadside unit and another truck, communication between a vehicle and the mobile network, communication between the vehicle and a cyclist, a pedestrian. So you can see there's different information flows in a VANET. So this leads us to a broader view of vehicle-to-vehicle communication. So there's vehicle-to-vehicle, there's vehicle-to infrastructure, vehicle-to roadside unit. So in general, we call it vehicle-to-everything communication, or in short, it's V2X. So instead of V2. So the definition of a VANET, a spontaneous and self-organized network where vehicles equipped with short-range wireless devices communicate with each other to allow communications with roadside infrastructure equipment and with other vehicles. Looking at the communication that we have in the VANETs, we can classify the communications into two main parts. One is intra-vehicular communication, and the other one being inter-vehicular communication. Inter-vehicular communication will be the main focus of our lecture today. But to do the inter-vehicular communication, you need intra-vehicular communication. So intra-vehicular communications is the communications that happens inside the car. So there's plenty of sensors in a car. There can be cameras, lidars, radars, and all other sources of sensors inside a car. And information is collected at the ECU of a car, and then we can transmit related information to other vehicles, and that's intervehicular communication. So what to communicate? We can communicate speed. We can communicate locations. We can communicate directions and accelerations of the vehicles. We can communicate events such as braking to our neighbors. Now, this is crucial in a vehicular network. The next thing that we can communicate is hazards, things like broken down vehicles, icy roads, slippery roads. So these are hazards and will be useful to communicate to your neighboring vehicles. We can communicate warnings, things like flood alerts, landslide alerts. Next is actions. Now actions mainly from roadside units to the car, things to do, things not to do, make ways to emergency vehicles, change lanes, things like that. And finally, infotainment. So infotainment stands for information plus entertainment. Now with autonomous driving coming into being a hot topic these days, infotainment will play a big role in the future. Now, when you communicate, the messages again can be classified into two main categories, event-driven and periodic. So each vehicle transmits these messages. Some are in a periodic manner and some are in an event-driven manner. I'll start with the periodic messages. So periodic messages, as the name say, are the ones that you transmit in a periodic manner as heartbeat messages. So the neighboring vehicles, the roadside units, and all the nodes surrounding the vehicle will be aware of the total network through these periodic heartbeat messages. So that will include speed levels, locations, and from this you can make the topology of your van. Event-driven messages are when an event occurs, say a sudden brake, or you have some sort of a warning, and you want to transmit that to your peers or neighbors. So those are event-driven messages. So most of these periodic messages are sometimes called beacons because they are broadcast in a periodic manner to your neighbors. So now we know what a VANET is, what we communicate in a VANET, what sort of messages we transmit in a VANET. And next, let's look at benefits. So most of these benefits we actually know from because we use the road network on a daily basis. Now, with proper or efficient vehicle-to-vehicle communications, the first thing that we can achieve is improved road safety. So we can use this for collision avoidance because the vehicles will be talking to each. So when we drive cars, there are many places in the road that we cannot see. They are not visible due to other large vehicles or intersections. And through communication, we can see these blind spots, or we can at least get an idea about these blind spots. So we know how to react in these cases. Hazard alerts, we already talked about it in the lecture. The next advantage is reduced traffic congestion. With proper vehicle-to-vehicle communications, we can get cooperative traffic flows. That is, all the vehicles drive in a cooperative manner so that we can adjust the speeds to reduce the traffic congestions in the road. And also we can do dynamic rerouting. Dynamic rerouting is we get the information about traffic beforehand and we can reroute vehicles along paths that have lesser traffic that we can use for traffic management. The last one is platooning. So platooning is when a set of vehicles which is going from a known start point or origin to a destination and they are traveling together. So platooning means we can let them travel together at close to each other with synchronized speeds. And this is again another big advantage of vehicle-to-vehicle communications, which leads to enhanced efficiency, especially in fuel and battery usage. We can make the traffic light coordination and the use of infrastructure more efficient as well through proper communications. The next advantage I would like to discuss is on autonomous driving, which is a hot topic these days. Vehicle-to-vehicle communication is actually the enabler for autonomous driving. The first advantage of doing proper communication is it will allow vehicle to see beyond sensor limits. Now, what I mean by sensor limits is, now if you take any sensor such as the LiDAR, radar, or cameras, it can only sense its vicinity. Now, with communication, we can have this thing called a shared perception. Now, say that there are 6 autonomous cars. Each one is sharing their perception with others. So we can have a global view of the vehicular network and we can make decisions accordingly. And we can do corporate maneuvering as well. What do you mean by corporate maneuvering is the vehicles get together and they jointly decide their driving patterns, lane changes, and things like that. A big advantage of vehicular communication. Next advantage, emergency vehicle priority. In preemption is making way for emergency vehicles, and then fast response times of emergency vehicles can be ambulances, police, fire trucks. And the last one being lower accident costs. So we will have fewer collisions as we have better safety in the road network. And also we have logs. We have our communication logs, which we can use for investigations and for research purposes as well. So there's lots of advantages of vehicular communications. However, there are complexities associated with communications as well. The first one being the dynamic topology. the vehicular network keeps on changing at a very fast speed. So this is a complexity when it comes to wireless communications. The second one being limited range. So most of our communication is wireless, actually almost all. So we can only communicate in a limited range. And there's lots of obstacles. That's our third difficulty. So surrounding obstacles, those are buildings, large trucks. So there's lots of clutter in this network, and we will rarely get a line of sight path between the transmitter and the receiver. So this is again another complexity. The fourth one is interference. Now all these vehicles are transmitting simultaneously. So we need to handle interference in the network. So what do you mean by interference is, say that you have a classroom of 40 students. All the students are talking at once, and you will not be able to understand what the individual student is saying. So we are having a similar situation in a vehicular network. All are transmitting simultaneously. So how do we handle the simultaneous transmission? Next, the QoS constraints with our application. We need very low latency. With that, we need very high reliability. Right? So these usually have a trade-off. So we need to manage that. We need it to be quick, and we need it to be reliable as well. Because if it is not reliable, there will be crashes. And if it is not quick as well, there will be crashes because they will be making decisions on expired information. The last complexity is security. Now, when you try for low latency, again, there's a trade-off between low latency and security. Right? And in terms of security, it's vital to have security in such a network, because if there is a malicious user in your network, the malicious user can create havoc in your network. So security is a complexity as well. And being required to do things very fast makes this security complexity much more tough as well. Now let's look at the technologies. There are two main technologies that support vehicle-to-vehicle communications. The first one is DSRC. So this is the most mature technology when it comes to vehicle-to-vehicle communication. This is introduced by IEEE. And the other one is cellular V2X. So this is introduced by 3GPP. Now most of you might be familiar with IEEE. So 3GPP are the people who are giving you 4G, 5G, or all these cellular. So IEEE networks came out first, right? So they stem on the very well-known Wi-Fi standards, and the most famous one being IEEE 802.11p, the latest standard being IEEE 802.11bd. Range is about 300 meters, and this operates on the 5.9 gigahertz band reserved for intelligent transport systems. So it's a dedicated frequency for DSRC transmission. And this does not require cellular network connectivity. So if you are using DSRC, you need to install these roadside units and DSRC devices, which most new cars have, in your cars, and you need to build up this infrastructure to support vehicular communication. So this is the motivation behind 3GPP's launch of cellular V2X. Now, what 3GPP is saying is we already have cellular connectivity. So with 4G and 5G, with 5G, we have very low latencies, and we can talk directly between end devices as well. So what 3GPP is suggesting is to use these cellular networks for vehicle-to-vehicle communication. So this can be used on top of the already available infrastructure, the 5G infrastructure. The most well-known standard is CV2X Mode 4, and the newer standard being CV2X New Ray. So these are the two main technologies that we have. They are competing technologies. IEEE has DSRC, it stems on Wi-Fi, and 3GPP has cellular V2X. There are hybrid approaches of these technologies as well. So hybrid approaches combine other short-range wireless technologies such as Wi-Fi, Wi-Fi Direct, LTE Direct, and Bluetooth to actually improve the penetration of vehicular communications. Now we know that DSRC and both DSRC and cellular V2X, the penetration levels of these technologies is very low when it comes to especially developing countries. So what hybrid technologies do is, okay, we have some sort of DSRC or cellular V2X connectivity, and from that point onwards, can we get an extra hop through other well-known wireless technologies? So those are these hybrid technologies. Now let's go to the more interesting part of the presentation, work we have done at Moratuwa. So my introduction, I can divide it into four main parts. The first one being concepts of V2V communications, protocols and algorithms. Then what are the communication protocols that we can use when we communicate among two cars in a particular application? What sort of algorithms that we have to use? That's part one. There's work on DSRC. There's work on cellular V2X. And there's work on hybrid technology. So we have been doing this work over about 8-9 years. We have had a huge team of students to do this work with us. And the ones on the right are the team leaders, the leaders of our group, which are very well known in Moratuwa. I'll start with the communication protocols and algorithms. So when we started this work in 2016, the first thing that we wanted to know was, we wanted to get an idea of how these messages are transmitted, how these protocols operate, and what sort of algorithms do they use in each of these applications. So we looked at many applications, some being corporate car following, emergency vehicle traversal, intersection traversal, and vehicle platooning. So what we wanted to do here was, say it's corporate car following. Now in a corporate car following scenario, how does the communication happen in a corporate car following scenario? What are the protocols used? What are the algorithms used? And for this, we based our study on a simulator. We use this VANES framework. So VANES is a framework which interconnects a network simulator and a traffic simulator. So traffic simulator is the well-known open source traffic simulator Sumo. And the network simulator is again the well-known network simulator Omnet++. So the VANES framework connects these two simulators together. Now for an example, so Sumo looks like this. Say that this vehicle wants to traverse the intersection. So to do that, assume that there's a roadside unit in the center of this intersection. This vehicle needs to first transmit to the roadside unit and get a green light for it to travel, or get the permission for it to travel. Now this message passing cannot be done in Sumo. Why? Because Sumo is a traffic simulator. So in that case, what happens is, through the VANES framework, it uses the Omnet++ network simulator to do these communications, right? So the simulation of the communication happens in the network simulator, and when the decision is taken, the green light is given to Sumo, and it will allow this car to move. So that's how this simulation platform works. I will probably explain a bit more about this platform a bit later when we look at examples. I will start with a very simple example. This corporate car following. So there's a leading vehicle here. It has its own acceleration and velocity. This is the lagging vehicle with its own acceleration and velocity. And there's a distance of d between the two vehicles. Now assume a case where this leading vehicle suddenly brakes and stops. Right. Now say that we want to implement this in the simulator. Now, when we want to implement this at the simulator, we have to implement what happens at the lagging vehicle, what happens at the leading vehicle, what sort of information should you transmit between the leading vehicle and the lagging vehicle, and how the acceleration should be set at the lagging vehicle so that the collision is avoided. Right. So these things are implemented in the simulator. Now, after you implement these algorithms, setting accelerations, and the communication protocols in the simulator, what we can do is we can evaluate the performance of these scenarios through the simulations. So here is one plot that I got from one of our publications. So in your x-axis, you can see the beacon frequency. So beacon frequency is the frequency at which the vehicles transmit the heartbeat messages with each other. Y-axis is the packet loss percentage. Now, when you have a look at the plot, you can see the failure region and the operational region. When the beacon frequency is low, you can see you cannot accept any sort of packet loss in the network. But when the beacon frequency is higher, that is, you are communicating more frequently with your neighbors, you can accommodate some sort of packet loss. Right. So these are the operational region, these are the failure region. So such performance evaluations can be done using this simulation together with implementing safety algorithms, communication protocols. So this is where we actually started our work on vehicle-to-vehicle communication. Looking at another example, say there's an intersection here, and we have a roadside unit. And what we want to implement here is, so these vehicles are approaching, we want to implement intersection traversal or intersection navigation. So here, looking at the communication protocol, so this is the communication protocol. So communication protocol is the set of rules which tells each vehicle, this is how you should communicate. And here what happens is, we start with the roadside unit. The roadside unit transmits an awareness message shown by these red lines. So each vehicle approaching this intersection will know that there is a roadside unit governing the traversal through this intersection. When you get this awareness message, each vehicle will transmit its request to the roadside unit. The roadside unit, depending on the available request, it will make decisions and it will give permission to a set of vehicles to pass the intersection. After passing the intersection, these vehicles will again send release messages to the roadside unit so they can forget thinking about it. You can explain it a bit more through an animation. Now this roadside unit transmits the awareness message to the car, the green car. The green car sends back a request and the roadside unit adds that vehicle into its queue. Now what the roadside unit did was it moved the pink color and the gray color request into the permit list. In the sense, the roadside unit gave permission for the pink and the gray color cars to traverse the intersection. And after they traverse the intersection, they transmit release messages to roadside unit. So roadside unit will stop thinking about it. Another example here where this EV, emergency vehicle, transmits its beacons to all the surrounding vehicles. All surrounding vehicles will respond to the EV depending on what it requests. And depending on the information, the EV made the choice of changing the lane. So after doing these simulations, we wanted to actually try these out with real experiments. So we got a very good idea of how these communication protocols are implemented, what sort of algorithms that they have in the transmitting and the receiving nodes. And we wanted to implement them and see how these things work. So we got down these both side units. So these DSRC equipment, we actually did the first DSRC experiments in Sri Lanka. So these are roadside unit, and we have installed the DSRC units inside the cars. You can see the antenna here at the top of the vehicles. And we implemented what we had in most of, like some of the stuff that we did through simulations in using real hardware. Now, while doing these experiments, we also felt that we need to go for hybrid technologies if we are to implement or make use of these sort of gadgets in developing countries, because the penetration of these things is very low in developing countries. So what we tried to do with regards to hybrid technologies is to tally DSRC with commonly available wireless technologies in the market. One thing that we looked in very detail was Wi-Fi. Now, obviously, when using something like Wi-Fi for our communications, it will be suboptimal because Wi-Fi is made for something else. So we had to spend a lot of time in integrating these two such that for all applications, you cannot use these hybrid techniques. But for some applications, you can use an hybrid approach and make use of vehicular communication. So what you have in the slide is something like this. An example, say that there's a train approaching, there's a DSRC unit on the train, and there's a DSRC unit at the gate. And from there, through Wi-Fi beacons, you notify the cars and all the pedestrians in that area. So if you here you want to further increase the range, you can have the receiver, you can move the receiver towards the incoming train and can have a wired line there as well. So these are examples of using hybrid technologies. So this is another one which we implemented using a final year project. Now, we call these active road signs. Now, the picture on your left is a flooded road ahead warning sign. Now, when there is this a temporary warning is there, we have to erect a warning sign like that. So what we tried to do was, alternatively, we have a Wi-Fi transmitter there, transmits the Wi-Fi beacons, and these Wi-Fi beacons are captured by the car and it's displayed in the car, and we call that active road signs. We tried many other approaches as well with regards to hybrid technologies, things like toll collections, pedestrian crossing warnings, where we integrated camera feeds as well. So did few projects on these hybrid technologies. Now, all the work that I told you earlier are mainly project-based and applied research-based. We did quite a bit of work on theoretical research as well. When it comes to theory, we wanted to do a decent comparison between the two competing technologies, DSRC and cellular V2X. Which is better and in which cases? So here what we wanted to do was we picked the MAC layer, which is the multiple access control layer. I will tell you what the MAC layer, what it means later. So we focused on the MAC layer and we use the tools that we use is discrete time Markov chains. Now, multiple access layer, access control is when multiple people try to access a common resource. Now, I already talked about this with regards to the road network, where different drivers try to access the road network. Now, when it comes to the communication environment as well, there are so many transmitters and they are trying to share the radio resources around them. Right? They are transmitting simultaneously. So when you are transmitting simultaneously, it's again like a classroom. There's 40 students. All of them are talking at once. If you don't have some sort of a protocol or some sort of a management inside the classroom, you will not be able to effectively communicate. So you come up with a protocol for that. Now, when you allow multiple people to access the common resource, obviously there will be delays, right? Because you can't ask everyone to transmit at once. You have to ask people to take turns. So there will be delays, right? And there will be collisions as well. What do you mean by a collision is more than one person transmit at once. So in the classroom scenario, more than one person talk at once. Right. Yes, we do understand that a protocol is there, but a protocol is made to minimize these collisions. Now, if you try to minimize or like totally mitigate the collisions, there will be a huge delay. So there's a trade-off between delay and collisions. So the next performance indicator that we wanted to study was collisions. And the last one being channel utilization. Channel utilization means we have this common resource of channel, how much of it is used and how efficiently are we using this channel. So for people who are familiar with MAC layer, DSRC is based on the well-known IEEE 802.11 family, so 11P. So it is based on the contention-based mechanism, CSMA, CA based, similar to what you have in Wi-Fi. CV2X mode 4 has a reservation-based scheduling mechanism. So the IEEE one is contention-based, where you content for the channel. CV2X mode 4 is a scheduling-based channel. What do you mean by scheduling-based channel is each vehicle is given its own resource to communicate. For an example, say take radio, for example. All radio channels are transmitting at once, but we are allocating each one of these radio channels a frequency. So we can separate these signals at the receiver. So what we are doing there is allocating them resources. So CV2X mode 4 is a reservation-based system such as that. Then you might ask how there can be collisions. The collision is because it's done in a distributed manner. In the sense, the vehicles will decide what radio resource I am going to pick. It's not governed by a central place. So since it's done in a distributed manner, still more than one vehicle can choose the same resource and there can be a collision. So this is the overall model that we have. We have a DTMC to generate the periodic traffic. We have another DTMC to generate the random traffic. So random traffic is for event-driven messages, and periodic traffic generator obviously for the periodic traffic. The message type for periodic traffic is called cooperative awareness messages or CAM messages. The event-driven messages are called decentralized environmental notification messages or DENM messages. So after these messages are generated, you put them in a queue. So this queue is modeled using a DTMC as well. Then we have a DTMC each to model the MAC layer operations of IEEE 802.11p and another to model the MAC layer operations of CV2X mode 4. So there's dependent parameters. So these DTMCs are connected with each other. So it goes in like this, comes out, and again they are connected with the generators. Just briefly show you how these DTMCs look like. I'll start with the traffic generator. give you a very high level idea of what is happening. So say these blue lines deal with the periodic traffic generation. So these where the packet is generated, it goes, after the packet is generated, it goes here, it waits a certain number of states until it comes here, and then it generates the next packet. Goes here, waits, and again generates the packet. The one we have here is, you can see that it's a Poisson process that we have. So the red lines and the black lines are for the DNM messages, where we generate the event-driven messages, and the black lines and the blue lines are for the CAM messages, where we have the periodic traffic. And when the packets are generated, we load them in the queue. Queue is another DTMC. Say that you are here. When a new packet comes, it goes to state 2. If you are here and a packet is being transmitted, then you go to state 0. So that's what happens here. So that's quite simple. And the next 2 slides is the main contribution of our work. Now, what we have done here is we have rigorously gone through the standards, the MAC layer standards of each of these technologies. We have understood how they are doing the mediation in the MAC layer, and we have developed DTMCs for each of these technologies. I will roughly go through. So these for CV2X mode 4. So these are wait, right? The vehicle will wait. These are random wait to start with. And then this vehicle will pick a resource. So this resource is called a CSR. When the vehicle picks a CSR, it randomly and uniformly picks a number between RA and RN. Right? So these candidate values for RA and RN are given here in this table. Say that you pick RN. Now RN means the protocol allows that vehicle to transmit RN times using the same CSR. Right? So when you get here, you can transmit. So this is called a transmission opportunity. If the queue is empty, it will go here and wait until you get another transmission opportunity. And then if you have a packet, you will transmit and then go to the next line. Wait, transmit, go to the next. Wait, transmit and go to the next until you get to 1, 0. When you get to 1, 0, so these are the red ones are the waiting states, yellow ones, transmission opportunities. When you get to 1, 0, you make a decision on whether to use the same CSR or to select another CSR and do your transmission. The MACLay operation for 802.11p is some of you might be more familiar with this because we have learned CSMACA. So here the red states are the transmission states. And before getting into the transmission states, there's a whole lot of states. There's waiting. There's waiting until another vehicle transmission is finished. That is, you sense the channel. If it is busy, you have to wait. There are these back-off stages. And again, all these are taken from the standards, and we have implemented those things in our DTMCs. Next thing that we do is we get closed form expressions for the steady state probabilities. Right? So for each of these states, we derive closed form expressions. Now the steady state probability will tell you on average how long or how much time you spend on each of these states. Now when you get an idea about probabilistically how much time you will spend on each of these states, we can calculate average delay values. And depending on how often you stay in the transmission states, you can calculate collision probability values as well, and also channel utilization values. So we derive these closed form expressions, we solve them iteratively, and upon convergence, we use the steady state probabilities to derive our required performance metrics on average delay, collision probability, and channel utilization. So these are some results and conclusions. 802.11p is better on average delay. CV2X mode 4 is better in resolving collisions, and it is also better in utilizing the channel. So what we can do is, like, these findings are somewhat intuitive as well, but through these models we can quantify these statements, in the sense how good are they. And when you change the parameters, when you change transmitting conditions, when you change applications, what happens, what's more suited, such comparisons we can do. And results have been published in IEEE Transactions on Communications. The next thing that we looked at is with multi-priority packets. Now, we already discussed that V2X networks support multitude of services. So they can be safety-related, sensor information, internet sharing. So depending on this application, to support different applications, we have different messages. We already talked about CAM and DNN. There are two more, high priority DNN and multi-hop DNN. And the priority is increasing in this direction. The next thing that we did was we extended our models such that it incorporates priority handling as well. So here you can see that there's generator each for each type of the packets. There's a queue each for each type of the packets. And we improved the MacLay operation such that priority is incorporated as well. So again, results in transactions on communications. And next, after we did these performance evaluations, we want to do some improvement to these standards. So since CV2X was the newer standard, we actually focused on the newer standard. Now, from these results, we saw that the IEEE version is good with delay. CV2X is not so good with delay. But the channel utilization of CV2X is very low. So what we wanted to check was, can we increase the channel utilization of CV2X and further decrease the delay in CV2X? And what we did was we studied on allocating multiple resources to each vehicle depending on their availability, and then we evaluated the performance. That is, we allowed vehicles to use multiple CSRs and again evaluated the performance. Results in IEEE transactions on intelligent transportation systems. Actually, in the newest CV2X standard, the similar concept is there. They have introduced this thing called numerologies, where the vehicles can, depending on what numerology the vehicle is using, they can use more resources on the physical layer. At the moment, we are extending the models for the latest standards, 802.11pd and CV2X Inaugural radio. Summing up, we are right on. So, I introduced vehicle-to-vehicle communications, advantages, technology, and finally ended up with work done at UOM. On top of vehicle-to-vehicle communications, these are some of the things that we have I have done in the past 10 years at Mortuor. Worked on wireless networks, intelligent reflective services, UAV networks, physical layer security, signal processing plus AI work, AI-based transmitter and receiver implementation, semantic communications, open radio access networks, and digital twins for wireless networks. So can see there will be a handful of publications on each of these topics as well. Finally, thank you very much for joining today. It's a privilege to be doing this talk in front of you, and thank you very much for joining.
Heartfelt gratitude to Professor Tharaka Samarasinghe for this insightful and compelling lecture on how cars talk to each other, future of safer roads. Your expertise and perspectives have undoubtedly broadened our understanding on this topic. As a token of appreciation to Professor Tharaka Samarasinghe and their contribution to this inaugural lecture series, I now invite to present a token of appreciation Professor Jagat Manatunga from the University of Monitor to present the lecture memento. Alongside, I would also like to invite Professor Samarasinghe to accept the lecture memento. Thank you, Professor Jagat Manatunga and Professor Tharaka Samarasinghe. Before we conclude, I'd like to take a moment to acknowledge and extend our appreciation to the esteemed sponsors of this 38th inaugural lecture. Hargreaves Private Limited, our event sponsor, Daily FT, the print media sponsor, and the Sri Lankan Scientist, our social media sponsor. With that, we officially bring today's 38th inaugural lecture to a close. Thank you all for being a part of this enlightening gathering. We look forward to welcoming you to the next iteration of this lecture series. Thank you once again and have a wonderful day ahead.